Thank you very much. I skipped to read the title again. Modern synthesis in green chemistry is of course used to synthesize complex molecules, and these syntheses often include new chemicals but also biocatalyzed transformations. And it is important for an effective application to know several details about these reactions, in particular in the field of biocatalysis, and we have to take a look to them more closely. So which details of biocatalyzed reactions are interesting? There are the solution structures of the starting materials, the progress of the reaction and the reaction rate in combination with kinetic data. There are parallel and consecutive reactions as well as metabolisms when we use whole cell reactions. We are interested to identify intermediates, but also on the binding of substrates, intermediates and products to the enzyme. That leads us finally to the reaction mechanism and to the structure of the products. And today I would like to address in the next 15 minutes these three questions which I have indicated here in blue. And the technique which we mainly use is the NMR technique as analytical method. And even by far now, 20 years ago, guys from biocatalysis said NMR spectroscopy is a window to the world of biocatalyzed reactions. As researchers, as guys from analytical chemistry or organic chemistry, we have of course to ask which details of the reaction can be investigated by NMR and which concepts and methods have to be applied. Taking a brief look to it, I have here a time scale from 10 to the 4th, 10 to the 5th seconds on the left-hand side and down to pico or femtoseconds on the right-hand side. And here we have the lifetime of different species of accumulated products, of isomerization products, of complexes formed during the reaction, and even of shorter events during the correlation time. NMR offers us only a very small window of frequencies by the magnets which are available, and the data which are available from the spectra are here in this region, so we also cannot cover all the questions which arise here. So we have to use different techniques, and today I would like to focus on two of them. One is direct analysis with in situ NMR, and on the other hand side, we have here saturation transferred difference NMR, which is in this time region. But let's take a look to in situ NMR briefly. There we run the reaction and no sampling is necessary. So the reaction is not influenced, and we have direct and substrate and product analysis during the reaction. The separation is made in the spectrum and not on the desk, and we can see almost all organic compounds because they all contain protons. So we do not need expensive isotope labeling, and we can measure concentrations down to meanwhile much less than 100 micromolar. But with plenty of light, there is some shadow. We always have to use water suppression because water is Mother Nature's decision for a solvent. D2O has to be added for a log signal, and we have only a small spectral width. One example for in situ is the hydrolysis of this acetopyruvate, here made by an enzyme from Pseudomonas putida. And we hydrolyze this CC bond resulting in pyruvate and the corresponding acid, and this is an enzyme in aromatic degradation. Taking a look to it, we see that our starting material has 3 different isomeric forms, and we can also see here in this in situ spectrum that we have 3 signals here, a little bit broad, and all 3 are consumed, while here the 2 methyl groups are, as in this case a methyl group, are the products which are produced. Changing that methyl group to a tertiary butyl group, the substrate is a little bit better accepted, and we have a much larger signal, indeed 3 times larger signals. And here we can see that the hydrate is consumed very slow, but the enol form, this form here, is consumed at the beginning, and then the isomerization between the diketone and the enol forms the enol and is then the rate limiting step. So here we have this reaction from this isomeric form, which is then made by the enzyme, and we found that out only by NMR spectroscopy. The other technique is saturation transfer difference NMR. Here we irradiate the protein over about 2 seconds on a certain frequency. Then spin diffusion through the whole protein leads to magnetization of all protons in it, and we have here an NOE, a dipole-dipole interaction, which then moves magnetization to all ligands which are bound during this time of 2 seconds. Then we make a 90-degree pulse and a spin lock for a T2 relaxation of the protein. And we can see here that the magnetization in the ligand is growing by the transferred magnetization and then transferred to the XY plane. Then we repeat the experiment without irradiation of the protein. So of course we have no growth of that magnetization vector here. And we have this little difference here, which indicates us the transferred magnetization and gives us information about the binding pattern. The premises are a small amount of the protein. We do not need very much, we need micrograms. No isotopic labeling is necessary, so we are again cheap and can start at an early stage when we are working on a new enzyme. And the measurements are independent of any knowledge about the protein or enzyme structure. And we get spatial closeness of ligand protons to the protein, binding epitope, of course, then of the ligands, and we get of course, then, as conclusion, information about the protein-ligand interactions. So, during biocatalysis, we are interested in substrate binding, in product binding, but also in binding during the catalytic process. And we have some by-side problems, that is co-substrate binding, coenzyme binding, and as we heard in the morning, mutations are important, the influence of mutations of the enzyme. And I would like to show now in one example the use of in situ and STD NMR for this enzyme, for the candidate tenuis xylose reductase, which reduces the aldehyde form of xylose to the corresponding alcohol, and it uses therefore NADH or also NADPH as source for the hydride. But it also accepts several other compounds like alpha and beta ketoesters and orthohaloacetophenones. But even for the natural reaction, which is catalyzed, we have a very high catalytic activity of 680,000 per mole and per second on the free form of the aldehyde of xylose. And taking a look to the in situ NMR, we see nothing curious here. We have consumption of alpha and beta xylose and production of xylitol as a product. But taking a closer look to it and changing the temperature down to 383 Kelvin, we see that we have a change in the ratio of alpha and beta xylose. And here we have then a higher concentration of beta xylose that changes then the ratio until the NADH is consumed. And then we recover to a certain point in between. And we make an interpretation of these data that only the alpha form is bound much better than the beta form. And then finally, when the NADH is used, even the alpha form binds better and is then better released from the enzyme. And The same is true when we change xylose to glucose. We have the same behavior, and also to galactose, which is also accepted by the CDXR. Running STD, the saturation transfer difference NMR, gives us some curious results or some difficult results. At the very beginning, it is quite easy. We have binding of the substrate, we have binding of the product, both with the NADH or the NAD+. But during the reaction, we have, of course, mixtures where we have the reaction which we would like to have, but also the substrate binds together with NAD+, and the product binds together with NAD, and we get there a mixture of the actual values. But finally, we have then only the product, and we can study that again. So we made an experiment in 4 steps with 4 STD NMRs over 1 hour. And we can follow here and see the change from the starting to, let's say, about half consumption of the reaction. And we see at first that we have at NAD+, which is produced quite high STD effects even at the beginning. This is the first time produced NAD+, which we see, which is then released by the enzyme. However, then the NADH is bound and released, but when it is transformed, it is not anymore available. So we have quite small STD here. And the same we have here for the substrate, where we have by far no signals, but here we have this, the product signals, and even at the very early beginning, we have good STD, and this is the product which is released for the first time from the reaction. Then we did several studies on it, and I don't want to go to detail. I only would like to show that when we use here xylose and the enzyme, we see good signals of beta-xylose and good signals of alpha-xylose. However, when we change then at the NADA, we see by far only the signals of beta-xylose. Alpha-xylose is not anymore available because it is transformed to xylitol. And changing then NADH to NAD+, we have again then the signals of alpha-xylose because we are not productive and have no transformation. That led us to make some docking, and we see the beta form does not really fit to the active site, but the alpha form fits quite well, and there we have the proof, now the third proof, that the alpha form is accepted better than the beta form. However, I said that also other compounds are accepted by the enzyme, and here we focused on the orthohaloacetophenones, which are shown here. And they are reduced then enantioselective to the corresponding alcohol. Here is an in situ spectrum of the reaction. And we can see here that we have only one enantiomer of the product. Taking a look to the STD NMR, which I don't want to show again because these are only very narrow signals, and here the docking experiment, we have a slight problem because we can very well show that the substrate fits quite well to the active site, and that we have then a reduction of the keto form to the corresponding alcohol in the right way. But on the other hand side, when we turn the molecule around, we are only half a kilocalorie worse than in this case, and that does not really explain why we have more than 99% of one enantiomer, of the S-enantiomer. And there we still have a little question, but that is more a question to the guys who make the calculations if there have been some more details involved. Why are we interested in that one? And that leads me now to a brief application. We can use it as a substrate for a PLK1 inhibitor, but also as a substrate for Oxetines, which are antidepressant drugs. And we focused on the second one, because that is a family of drugs which is very well known. You probably know Prozac, which is fluoxetine, and the comparable compounds nisoxetine and tomoxetine. They are worldwide used as antidepressant drugs, have a sales volume of in the billion-dollar region, and applied in the erythrocymic mixtures. Of course, both enantiomers have different effects, and so we have side effects which lead to intensive critique, probably well known from common discussions. We are now interested to make enantiomerical pure synthesis using CDXR, and have then a couple of reactions from easy available starting materials, here always with the chlorine. That was interesting at that moment in which we started that reaction, and here we have our final reaction of our final product, and we have always some preparation step, then the CDXR step, and then steps to the product. And we started with some long ways and made these ways shorter here down to 6 steps, again 6 steps. Here we have only 4 steps, and finally we started with the autochloroacetophenone, which I mentioned before, and then we come in 3 steps using the CDXR in a key step to our product. And we are working on that as a patent application, or now as a patent and marketing, since 3.5 years, and we have now the final patent since May. So that has not been done alone by myself, but I have to address my thanks to several co-workers at the University of Vienna, working in the lab, running the NMR, and from the calculation group, from the theoretical chemistry. And the enzyme is produced in Graz Technical University in the group of Bernd Lidetzky, and these colleagues are working with the enzymes, which I have shown, and I also would like to express my thanks to Herfried Kringel and Doug Ribbons, who started these ideas around 20 years ago. And of course, I have to thank you for your kind attention, because I think I have stressed my time too much.
Hey, we got time for one question. One question, please. Okay.
Did you patent your enzyme which is used for asymmetric reduction of ketones?
No, we patent the use of the enzyme and the synthetic way to the oxetines. We have not patented the enzymic reaction.
Okay. Have you done any substrate scope study where this enzyme is quite useful for reduction of ketones and so many other substrates? Apart from...
Yes, okay, you are right. That is for sure true that there are other applications, but we had the wish from both universities, which I have shown, to focus on this certain point, and so we started to patent only this particular part there. But you are entirely right. There are several other applications, in particular using the 2 other groups of artificial substrates which I have shown.
Okay, thank you.